All right, welcome back, folks. So right now we're going to be diving into Big O notation, or algorithmic complexity analysis. So let me just give you a brief introduction for those of us who've never encountered this topic before, don't know what's going on. So Big O notation is used in programming to describe the relative performance of an algorithm. So this doesn't measure the specific performance of an algorithm, like how many seconds an algorithm takes to run, or how much exact bytes of memory it consumes when it runs. But rather, we're interested in relatively how does the algorithm get slower or use up more memory as the input size increases. So there's kind of two kinds of algorithmic complexity that we might talk about. So if we were concerned about how the algorithm gets slower, it takes more time as the input size grows, that is time complexity. And then sometimes you're worried about the memory that your algorithm takes up. How much stuff does it have to remember at one time? This is referred to as space complexity. Usually, though, we're focused on time complexity when we talk about complexity analysis. It's kind of assumed that we have enough memory for whatever algorithm our program is trying to run, but we never have enough time. Because if you can make an algorithm run in half as much time, then you can just run it twice as much. So we always want things to go faster. I saw a question real quick. Well, it doesn't have to be quick. What's your question?
I'm just curious. So you guys push all this to the Romeo Platoon GitHub. When we're done with the course and we go for interviews, are we still gonna have access to these same to the GitHub? Can we review these notes also once it's over?
Yeah, I believe that you should always be members of the Romeo Platoon GitHub. So you should be able to refer back to your course materials.
Cool. Thank you.
So notice here that I'm talking about as the input size grows. So generally speaking, in these kinds of algorithms that you might analyze using complexity analysis, we're talking about algorithms where you take an array as input. So there's some list of data that you need to process, and you're worried as the list gets bigger, how much slower does this algorithm become? Specifically, as the input size gets ridiculously large, like hundreds of thousands, millions of elements, as it's trending towards infinity. We're talking about the asymptotic growth of an algorithm. So when we measure the complexity of an algorithm, there are a few assumptions we have to make, first of all. So you're actually going to like this because this makes our job a lot simpler in a lot of cases. So First assumption that we make when we're analyzing the complexity of an algorithm is we're only concerned with the worst case scenario. So there are a lot of algorithms that like a sorting algorithm, for example, if you try to sort a list that's already like almost sorted, maybe there are some algorithms that can do that really quickly, but then if you give it a different list that's like totally mixed up, then that algorithm does really poorly and it takes way longer. Whereas there are, better, more popular sorting algorithms that are able to sort arrays relatively quickly in all cases, no matter how mixed up the array was to begin with. So we're always going to be pessimistic when we're doing our complexity analysis. We're worried about, for the very worst input that is the hardest to process, how long does it take us to process that input? So we're only looking at worst case scenarios. So also kind of an interesting thing about Big O is that even though I said we're very much interested in the time our algorithms take to complete, we're not actually going to measure anything in seconds or milliseconds or whatever. We measure the time in number of operations and then just kind of assume that every operation takes the same amount of time. So commonly, like you're just counting how many iterations of a for loop have to happen in order to like successfully run a function. That's kind of what we mean by number of operations, like just number of if checks, number of loops or iterations of a loop. Oh, and again, please ask many questions. This is maybe not the most straightforward stuff. And it's kind of hard to know how to explain, like where's the beginning to start from. Depends on, some prior knowledge maybe. Jake, what's on your mind?
Yeah, I might have missed this, but what does the O stand for? Like, what does Big O stand for?
That's a great question. I want to say it's like a Greek letter, actually. It's not like an acronym for an English word.
Okay.
It's actually part of like a family of different like complexity terms. So like in addition to Big O, which is like the upper bound, then like, Big O is upper bound, Big Omega is the lower bound, Big Theta is some like middle bit. I don't know. There's different ways to talk about the performance. So other than Big O is specifically the worst case scenario, which is generally the most important, the most interesting. But yeah, it doesn't stand for a word. Or
Okay,
if it does, I don't know what it is.
That makes sense. Thank you.
Uh-huh.
Hey, so Evan just put in the chat what it stands for.
Oh, am I going to learn something? Oh, that is incredibly useful. I mean, thanks for sharing that. Now I know, but I'm not sure how I'm going to apply that to my day-to-day programming.
Alicia had a good question in the chat, and some people are throwing in answers. But she was asking, like, what does worst case? I don't want to speak for you, but how do you isolate the worst case scenario of a hypothetical problem?
I mean, sometimes I think it takes a little creativity. Maybe I can't always imagine what the worst case scenario is by looking at an algorithm, but I think there's some examples here in the chat that are really good. Oh yeah, Adam, your example is probably the simplest one. If you're searching for an item in the list, it's possible that the item you're searching for is the first item in the list and you can find it in just one operation, just one check looking at the first item in the list. But in the worst case scenario, the item you're looking for is the last item in the list. So in that case, you would have to do as many checks as the length of the array. So that's the worst case scenario that we want to prepare for, that the item we're looking for is at the end of the array, not at the start.
And my understanding, and I could be wrong, but my understanding is the reason we generally care the most about worst case is because that's what takes the longest. So if we calculate for that and kind of always assume worst case, then we generally, everything else is going to be better. There are cases where sometimes you care more about average case or best case, but for like interview purposes and when people talk about complexity, they're always talking about generally big O, like worst case.
Mhm. Yeah, that's a very good point. And honestly, I'm kind of a contrarian when it comes to big O analysis. So I'm telling you here what the assumptions are for how you do this classically, academically, what people will be expecting of you in interviews. But there are practical reasons that I'll discuss at the end of this lecture why these assumptions are not always true. But for now, we're just going to go with them. So the last assumption that we need to understand before we start measuring complexity is that only the largest term matters. So let me just show you an example real quick what I'm talking about. If we have an algorithm that processes an array, let's say the length of the array is n. Maybe we could describe the complexity of this algorithm like mathematically as 3n squared plus 4n plus 1,000. So we're saying that like no matter how big the array is, we have to do 1,000 loops just to get started. And then we also have to do 4 times the length of the array, that many more loops. And then also the length of the array squared times 3, we have to do that many loops also. So, mathematically with this kind of algebra, you could describe how many iterations in a loop you need to do in order to like successfully perform some algorithm. But this is more complex than we care about when discussing big O analysis. Because again, we're not really interested in arrays that have 10, 20, or even like 100 or 1,000 elements. We're concerned about, hundreds of thousands, millions of elements, close to infinity. So even though, when n is 10, this 1,000 is way more meaningful than 4n or even 3n squared. But as n gets, any higher, especially in the hundreds, thousands, or whatever, we will very quickly stop caring about this 1,000 or even this 4n, and only the very biggest, most influential thing matters. So here we don't care about the 1,000, don't care about 4n or even the 3. It's just, this is n squared. So if you worked out the math and you determined that this is the number of iterations of your loop need to happen in order to process a given array, and someone asks you, what is the complexity of that algorithm? You would say that it is O of n squared. So the way we talk about these complexities is much simpler than like the reality of the situation. Yeah, so at this point, I would like to show a couple of different algorithms, and let's talk about how many different checks or how many operations do we think are needed in order for this algorithm to run successfully for arrays of different sizes. So we're starting off simple here. So we've written a function that just appends an item to a list. So I'm going to pose this question to the class. How many operations, generally does it take to run this function? And how does that number increase as the size of my list increases?
I think it's going to take one operation, and it's still going to be one as the size of the list increases.
Not going to disagree with you. Evan, do you have any thoughts?
No, not particularly anything different than what Rex said, so never mind.
So yeah, Rex, you got the right idea. It's just one operation to add this to the end of the list, and that has no bearing on how big the list is, whether it was one item or a million items. It's one operation to append to the end of it. So we would say that this is this is O of 1, also known as constant time, because it takes the same amount of time no matter how big the array is. So remember, when we're talking about Big O notation, the variable n is used to describe the length of the array. But so here, n isn't included at all, which means that this algorithm doesn't depend on the length of the array. Evan, did you have a question?
No, sorry.
Cool. So let's look at another algorithm here real quick. Okay, so pretty simple algorithm here. We're going to loop through my list, searching for any item that is bigger than value. And when we find it, we return true. If we get through the whole list, we don't find anything, we return false. So let me again ask the class, what is the complexity of this algorithm? Or how many iterations do we have to make based on the size of my list? Michael? You might be muted.
So I think in the worst case, we're going to have to search through every item in the list. So I would say Big O of n.
Yeah. So again, n is the length of the list. And worst case scenario, we're going to have to make as many checks as there are items in the list. So this is O of n. Call this linear time. So moving down the list a little bit. Evan, got your hand up?
Yeah, I was just anticipating you calling on somebody for the answer to this one.
Yeah, Evan, what was your question about the last You, in the chat, was it about the problem that Raphael was just showing? I didn't quite understand.
Yeah, it was just in general, more as like end to the end is pretty bad. So would you be like more impressive? Yeah, never mind. Just disregard. Sorry.
Yeah, I think I get what you're saying. I think the path to go on is what people are looking for is that you understand the concept and are on the right path to understanding the algorithm correctly.
So sorry if I'm slow on the uptake here, but where are people getting these? Like he said, I can't remember who answered, but they said O to the N or whatever. Like, how are you guys knowing what these are referenced as?
So all that we're worried about here is inside these parentheses, if n is the length of the array, how many iterations do we need, worst case, in order for this algorithm to complete? So if we need to make as many iterations in our loop as there are elements in the array, then that's just n.
Okay,
So maybe as we get to some of these more complex ones, you'll get to see
that
some.
one makes sense to me.
Are we still using the small list array? Like at the very top?
Yeah,
Okay, so would it that like O of n, would it be just like O of how like 5? Or does that not work?
you don't really talk about it like that because you're always assuming, like this is always a general way to describe the algorithm itself, because it might potentially be called in the future with a larger list. Like this is just the test data here incidentally, but I could have used, you know, a big list also. So here the big list is twice as big as the small list. So for our append to list, this function should take just as long on small list versus the big list. But for find item greater exists, it should take twice as long on the big list as the small list because it's twice as big and it's a linear algorithm. But it's going to be a little bit different for this find double exists. So this function, giving a list, it iterates through the list and will tell you if any number is twice the size of any other number in that list. So does anyone want to take a stab at this? What's the complexity here? If we have, yeah. So again, if we have n items in our list, we're going to have to perform n squared iterations because we're looping over the same list inside of a loop of that list. So yeah, if the list is like 3 elements long, we have to loop 9 times in order to check every element against every element. 5 item list, we're looping 25 times to check every element against every element. Is that clear to everyone? All right, we'll continue then. Garrett?
Can you hear me?
Yep.
A little bit confused about whether like n is the number of inputs or the amount of space they take, because wouldn't that change like if one of the elements in the list was like a really large number and each calculation performed with it would change the efficiency more than the other elements in the list?
Practically speaking, you're correct, but that's not how we do Big O analysis. We're
Oh,
assuming
they just assume that they all like are around the same memory, kind
yeah,
of, so you can like use the
Yeah.
number of inputs or the memory.
right.
interchange.
Everything takes the same amount of memory. Every operation takes the same amount of time.
Okay. All right.
A
Thank
lot
you.
of assumptions here.
Yeah. Yeah, and you can just pretend like we were talking about arrays as a data structure yesterday and how like the way that like there's a, you know, integer is like a primitive type, and an array of integers, every element in that array is going to have the same amount of space, whether the integer is small or big.
Well, I was asking about the case because you can have elements that are different. Like one could be float.
Right. That's, you're not going to see that in these kind of problems. Both because of the conventions of the problem, like Ralph was saying. Yeah, sorry, I'm going on a bit, but sorry, Raphael, I don't know why I keep doing that. Yeah, the conventions is that everything is sort of the same.
Okay, thank you.
So I'm going to show you another algorithm real quick here. You might be familiar with this, but we haven't discussed the complexity of it before. So it's probably a little bit hard to work out in your head what the complexity of this is, but I don't know if anybody wants to take a stab at it.
Makes a tree. I mean, it's 2 to the n, but every time you call the function, you're creating 2 offshoots. So each one of those 2 offshoots is creating 2 more offshoots, and each one of those 4 offshoots is creating 2 more offshoots. So this is where it becomes a 2 to the n. So depending on how many times you're iterating through it, it's going to effectively double in size every single time, which can get out of hand really quick.
Yeah. So
That's why it's hard to calculate Fibonacci of like anything higher than 40 or 52, I think. 50, like I think 52 is technically infinity.
well, so using the recursive algorithm, it's particularly inefficient.
Oh, not a,
And so, yeah, that's going to be 2 to the n. So if, you know, you've got 4 items in your array, that's what 2 to the 4th power is 8, 16, 32. So yeah, it gets really slow really quickly as the input becomes larger. Or I guess this isn't an array that we're processing, but it's still a similar concept. We have to do more looping, more iteration in order to compute a larger Fibonacci number. So that's a similar problem. Now there's a couple of other time complexities that I want to talk about, but I'm not going to show you any algorithms for them. One, because it's a little bit too complex to demonstrate, and then the other because it's your homework for tonight, so I don't want to give away all the secrets. But so there's another time that kind of falls in between constant time and linear time. So there's also log O of log n. So I'm not going to explain what logarithms are because this is not a review of math class. But basically, O of log n is it's faster than linear search. So this describes doing a binary search actually. So we've mentioned this before, like imagine if you have a phone book and you want to find a particular name in the phone book, you could just search through every name one by one until you find the person you're looking for. And that's a linear complexity algorithm. So it's not too bad. It's O of n. But if you're using a sorted phone book, everyone's name is in alphabetical order, there's a better option. Instead, you just open to the middle of the phone book and find the middle name, and then ask yourself if the person you're looking for is before or after that. And so then if it's, you know, before, for example, you take that first half of the phone book and then split that in half, and then repeat the same process, checking if the person you're looking for is in front of or behind the spot that you opened it to. And so this dramatically cuts down the number of checks that you need to perform. The way that I think about this is that whereas with a linear algorithm, adding one element to the array adds one operation. Whereas with log n algorithms, doubling the size of the input adds one operation. Because I mean, like, think about it. If you've got a phone book that has 1,000 names in it, and we know that takes a certain number of operations in order to find the person we're looking for, because we're able to cut it in half on each operation, if I doubled the size of the phone book from 1,000 people to 2,000 people, like conceptually, that only takes one extra operation to handle that. Because after the first cut in half, then I'm left with a phone book that's the same size as I had before, 1,000 names. So without reviewing high school math and what exactly logarithms are, I think this is the simplest way to understand logarithmic time, is that you can double the size of the input and add only one extra operation. So yeah, binary search is a good example. And I believe you are going to be challenged to do that for your homework tonight. And then there's one more, which is not the logarithm of n, but it's n times the logarithm of n. Yeah, people just call this n log n, basically. So this is important because it's not as fast as linear time, but it's not as bad as quadratic time. And like, in my opinion, quadratic algorithms are just too slow to be used professionally. Like, unless you can guarantee somehow that your input is never going to be larger than like 10 or 20 items, it's just inappropriate to use a quadratic algorithm for work. So I would say that like n log n algorithms are interesting because these are the slowest algorithms that you can actually use practically. Also important to know is that the best modern sorting algorithms can sort an array this fast. So it's important to know that no matter how like randomly shuffled up some array is, it's always possible to sort it in n log n time. And so that becomes really important because sometimes you're trying to solve a problem with an array that is very hard to do on an unsorted array. Like maybe the algorithm on an unsorted array would be n squared or 2 to the n, but the algorithm on a sorted array would be linear or n log n. In that case, it would make sense, instead of struggling through solving the problem with an unsorted array, just sort the array first and then do a more optimized solution that only works for sorted arrays. Because, to repeat myself, sorting an array it can be faster than many other like very slow operations, and it can make other things much faster to work on that same array. So this is kind of one of my little like interview tricks, I guess. Like if you're giving an algorithmic problem and someone challenges you to improve the performance of it, and you're not really sure where to begin, like consider sorting the array and then seeing if there's a simpler algorithm that you can apply to the sorted array, because sorting the array itself is probably faster than what you would try to do otherwise on an unsorted array.
That's great advice to, yeah, think about like sorting your data.
Okay, so this is a lot to talk about. Let's get some visualization of this stuff here. So this Big O cheat sheet, this is a great website. I've actually seen this particular graphic just like copy and pasted onto a whole bunch of other articles about Big O notation. So it might be familiar, you might see this. I think some of the scale here is a little bit weird. Like I can't really tell the difference between O log n and O of 1. They look like they're right on top of each other. But I know that O log n is slower than O of 1. But this still shows you that it's very fast. It's faster than O of n. This is linear time. And then here is O of n log n, which is not quite as fast as linear. You can see the number of operations increases more quickly as the elements increase. This line has a slight curve to it, curving upwards. So it's not a straight line like O of n. But at the very least, it's dramatically better than O of n squared. So these guys over here, n squared to the n factorial, these are horrible complexity. Like you just can't responsibly use these for professional purposes. So you'll notice there's this huge gulf here between n log n and n squared. Caleb, did you have your hand up?
Yeah, so is this safe to assume that any algorithm that has a sorting function inside is automatically n log n in terms of Big O notation?
That would be my assumption, yeah. Like given that it's possible, I don't know why like JavaScript or Python would use a less efficient sorting algorithm.
Yeah, agreed. I have no idea what they are, but I've always assumed that they're efficient.
I know I did look this up at one point, the actual sorting algorithm that JavaScript uses, and it's like some modified version of a popular algorithm. I want to say it's Tim sort. It's like some guy named Tim came up with some optimization to, I think it was quick sort, and then named it after himself. Anyways. So this is, I think, a really useful visualization of common complexities. Just knowing the ones in green are good, the ones in red are bad. I really appreciate the value judgment here. Helps you know how you can feel about your code. Down here is another useful table telling you about how Big O relates to different data structures and how long it takes to perform different operations. Excuse me. But some of this might actually be a little bit unintuitive because it's making some kind of odd assumptions. So first of all, looking at the array, this should be pretty familiar. We can access any element directly if we know its index. But other than that, the worst case for searching, inserting, or deleting an element requires us to traverse the entire array. So that's O of n. Or I guess that does say average case. Yeah, anyways, Justin, did you have a question?
Yeah, so you talked about the quadratic time n squared, and even according to the chart, that's a really bad thing to have.
Mm-hmm.
So n squared, you represented it by a nested for loop. But would the n squared apply to me? The n squared notation really would only kind of apply if your arrays were of a dynamic length and there was the possibility of making them bigger, right? So if you were adding and subtracting from that array. But if it was a static array size and you were double for looping through it, then that functional act is the same every time you do it because that array never changes size.
Mm-hmm.
So but do we still consider that a n squared Big O notation? I mean, when we're writing code, it sounds like you just want to avoid a nested for loop if your data set that you're looping through is subject to change size. That's when you run into an n squared situation, right?
Yeah, that's a really important observation, I think, that we're only concerned with the execution time as the input grows. So if you know that the input is not going to grow, then it's not a Big O problem. So I think this is a pretty common gotcha I've seen in like interview questions. They'll give you, you'll have a function that's like looping over my list and it's the input. So that could be of any potential size. And then inside of that, you're doing a loop over like days of the week. So it is a nested loop, but there's no reason why you'd ever append to days of the week. Like there's 7 of them and that's it. So you know that that inner loop is just going to be 7 loops. So your complexity for that algorithm, you could describe it as 7n. Because for every element of the array, you're doing 7 iterations because you have to do every day of the week. But yeah, that doesn't increase worse than linearly as your input array gets larger.
Yeah, I would even add, and Raphael, let me know if you think, if I'm off base, like when you're writing code for things that aren't like algorithm programming problems, don't worry about nested for loops unless you have like a lot of data. It might be like a code smell that there's a better way to do something, but practically, like, unless we're looking at like really large amounts of stuff, there aren't like real world performance concerns.
Yeah. I mean, I've only seen it once in my career where Big O analysis was relevant. Like somebody made a mistake that you could describe with Big O. And that was just in 2 lines of code. We had queried like all the records from our database, like every user in 1 array. So potentially very large, depending on, people signing up over time. And then mapped over the array, and then inside of the map callback, filtered the same array. So it's not as obvious looking at that because you see, the function calls map and filter, but you've got to know that under the hood, like the only way that map works is because it loops over all the elements one at a time and applies your function to them. And the only way that filter is able to work is because it has to loop over all of your array elements one at a time and apply your filter logic to it. So if you're filtering an array inside of a callback for map over that same array, that's a nested loop on 1 array. So that's going to be an n-squared algorithm. So yeah, that was a big production problem, and we had to like get all hands on deck and figure out how to rephrase that nested loop so that it didn't like bring down our whole application or whatever. So that was a fun time. But normally, Big O is not describing the kinds of practical problems you're going to have.
Yeah, I don't think I've ever run into one. I think it's kind of cool that you did, Raphael. And the database is a perfect example. And it's a good example of why it's good to know about this stuff too, because databases, like when you're interacting with MySQL or Postgres or like a relational database in a production environment, like those databases live on some server somewhere else so often. So it's slower to access the database and make requests and get data from it. And it has a lot more data. And so that's when like performance concerns actually start to matter, especially because your database query for like get a user or get all users or find this account is going to be used all the time. And it's really common for people to write not very efficient SQL that affects performance. So that's a great example. And I think a really good example of why, even if we never use this stuff, it's helpful to know about, so that when you're sitting there writing your SQL, you're not like, oh, I better have this complexity, but the basic ideas of how efficiency works, and you have a reasonable guess as if you're writing an efficient SQL query or not.
Yeah, definitely. So as we're looking over these common data structure operations, there's just a couple points I want to make here. So for one thing, I want to take a look at, where is it? So this is touching on something I said yesterday, the binary search tree. In the average case, binary search trees let you use binary search. That's what they're named for. And so searching through it or inserting, deleting things is going to have a log n complexity. So that's really great. We can double the size of our tree and only adds one extra operation for our search. But that's in the average case. So I was telling you how if you insert the nodes to a binary search tree in order, it actually just becomes a linked list. And so we can actually see here in the worst case scenario, access and search is O of n, which is the same as for a linked list because it is a linked list in the worst case scenario. Interestingly, then insertion and deletion are worse, actually. They're O of n, because as a binary search tree, we can only insert and delete things in the sorted order. So we have to make sure that we're doing it from the right location. Whereas a linked list, we can just add something to the end. It doesn't matter. It's not a sorted data structure. So I think that's kind of an interesting comparison, or just knowing that binary search tree, worst case, is a linked list. Also, something I want to point out is the hash table. So I made a big point the other day about how a hash table is great because it lets you efficiently access your data. If you have a key for a value, you can just hash the key and then it returns that value to you. You don't have to iterate over every element in the underlying array. You don't have to iterate through all the key value pairs. You just directly get the thing that you want. But if we look at the worst case here, it says everything is O of n. That in the worst case, or sorry, for the hash table, it says everything is O of n. That, getting one element that you need is it's going to take as long as the number of elements in that hash table. And so the reason for this is just kind of an obscure sort of tidbit about hash tables. But remember, I was talking about hash collisions, how when we generate a hash, there is some small random chance that two different keys will produce the same hash. So more sophisticated hash table implementations have a way of disambiguating that. So if there are multiple keys that produce the same value, instead of overwriting the previous value, overwriting the previous index, like what my implementation does, it would actually store a linked list as the value, so that if multiple different keys produce the same value, you can then traverse this linked list, and that can get you the correct value for the key that was requested. So the worst case scenario for a hash table is assuming that there is a hash collision for every single key. So in that case, your hash table is basically just one giant linked list under a single key, which again, that's like an incredibly unlikely situation that every single key that you add to your hash table collides. But that is technically the worst possible scenario that can physically happen. So here it is in the worst case scenario. So I know this was very confusing to me when I was looking at this table for the first time. I couldn't quite make sense of it, but I'm pretty sure that that's the assumption here, is that in the worst case scenario, every key that you add is a hash collision. And in that case, your hash table has basically become a linked list. And then here we have some sorting algorithm complexities. So in this bootcamp, I'm not going to encourage you to manually learn these sorting algorithms. Maybe if you were taking computer science at university, they might have you learn a bubble sort or like insertion sort or something, or maybe even merge sort. So these are algorithms that you could learn and memorize and write by hand. I don't think it's particularly important. What's good to know is that the sorting algorithm that you use in JavaScript or Python is going to be using something that is at least this good. I don't know if it uses heap sort per se or merge sort, but it's going to use some sorting algorithm that achieves n log n performance in even the worst case. So you should trust that that's something you can achieve. If you really wanted to learn one of these by hand, of all the like best sorting algorithms, I think merge sort is probably the easiest to learn to do by hand. But again, it's totally not necessary. What questions do we have? At this point, this is all I have to say about Big O notation. So we can just totally open up for questions, whatever you're curious about. I expect many people are confused about many parts of this, so please. Sorry, Danielle, did you raise your hand just a minute ago?
Oh yeah, I think you touched on that, on how to add them up, or what happens if you have like one operation that's O of n followed by another O of n, or if one O of n is nested in another O of n, like how do you add them up?
Yeah, so that relates to what I'm talking about here. Only the largest term matters. So if you're saying that we have one operation that's n, and then we do another thing that is also n, so we don't call that 2n, that's just n. So for example, so here we're doing a loop through every item in my list. And then afterwards, we're doing a loop, worst case, through every item in my list. So this is n, this is also n, but since it's not a loop inside of a loop, it's just two loops, you could say that this is 2n, but we don't care about the coefficients. We only care about the largest term. So it's n and whatever power it's raised to. So yeah, we would just call that n.
Right, and in the case of the quadratic one, if you nest again, for example, like instead of one after the other, if you nest them, like you have two nested for loops, like if for some reason you nested another loop that was O of n.
I guess that's n cubed.
Right.
Sound good?
Yes, thank you.
Skylar, did you have a question?
Yeah, I guess it's about the double for loop. So it's like if we can't do anything about it, then we're just kind of stuck with that double for loop essentially. Or are we going to just try our best to avoid those? I guess since they're awful.
An n squared algorithm.
Right.
I mean, so first of all, like you're talking about practically, you should ask yourself, like, how big is the input going to be? Like, is this actually going to be like thousands and thousands of elements? Like, yeah. I once had to write an algorithm for like people working at bars or restaurants. And this could potentially serve people that worked at multiple different bars, and multiple different shifts throughout the week. And I needed to iterate through all of their different jobs and perform some logic. And for that logic, I was not at all concerned about Big O complexity, because there's no way someone can have thousands and thousands of jobs, let alone dozens. Like they're going to have fewer than 5 at the most. But in that specific situation, since I had strong expectations about the input size, I would have been content to use an inefficient algorithm. But so for other situations, if you can't guarantee that, like definitely see if there's a more clever way that you can solve the problem so that you don't have to do that nested for loop. Oftentimes, like kind of a naive solution is going to have a nested for loop. But if you understand the specifics of the problem a little bit better, there might be shortcuts you can take. And that's going to depend on just the specific problem. I think you're going to get challenged on that a little bit tonight. Not sure. And if you can't come up with anything clever, then just tell your boss it's not feasible. Sound good?
Yeah, and I just want to say we're moving through this stuff very quickly, so it's really natural to have questions and not be sure of stuff. So please keep asking questions, and I think the more we do it, it'll get better. But definitely, if yeah, folks have questions, you're probably not the only one wondering.
Yeah, for sure. This would normally be like a semester at university. We're condensing it into an hour. It's kind of
Yeah.
absurd.
This is like a course.
Yeah, absolutely.
Skylar, to answer your question, Big O is just a general computer science concept that is used to look at algorithms for programming, no matter what the domain is.
Let's see, and I want to elaborate a little bit on Danielle was asking about just how we condense these numbers, like if it's a loop and another loop, like what do you call that? Is that 2n? So because of like, we don't care about coefficients, we don't care about like smaller terms or constant factors. When someone asks you a question, like what is the complexity of whatever algorithm, the answer is going to be one of these things you see here. It's going to be O of 1, O of n, O of log n, O of n log n, O of n squared, O of 2 to the n, or O of n factorial. So anytime someone asks you, like, what is the complexity of some algorithm, consider it a multiple choice question, basically. Because the algorithm itself is going to be more complex, but it's going to boil down to one of these options here. Oh, and then one last thing. So I did mention at the start about these assumptions. Generally, like these are the assumptions we make in Big O analysis. They are not always true. Some people would argue that they are always not true. But whatchamacallit? So a lot of the times I would say the average case scenario is more important than the worst case scenario. Like imagine page load time for visiting a website. Like everyone has experienced a page that fails to load or just randomly takes 10 seconds. And when that happens to me, like I'm not sure if that was the website that just randomly was struggling with something, or if my home internet like blinked out for 5 seconds or something. I have no idea, or maybe it was my computer itself had a problem. I have no idea why that web page failed to load that one time. I might just reload the page and then see if it works the next time. So that worst case scenario, like I might not be sensitive to that. Whereas if the page is kind of slow every time it loads, the average case is mediocre, I'm probably just not going to use that product. Assuming that all operations take the same amount of time, so this is actually not true. Bigger numbers like are harder to process for a computer, and just in general, other operations can be more expensive than some. So I think a particularly funny example of this is with the Fibonacci problem. So I showed you the recursive solution, which has really poor performance. It's 2 to the n. There's also a linear solution to the Fibonacci sequence. Let's actually just scroll down to that real quick. Don't need to make you watch me type it out. Okay, yeah. So it would have been nice if we didn't have one-letter variable names, but this is a linear solution for the Fibonacci sequence. It does one for loop up until n, or n minus 1. But so you can see here, since it's just a single for loop, the number of operations we perform is always going to be equal to n minus 1. So the Big O analysis of this algorithm should be n. Now, I haven't tested this, but I've read that apparently this linear Fibonacci algorithm still gets worse than linear performance, because the numbers that you're adding up get so much bigger so fast, and it literally just takes more time for your computer to add up such large numbers. And like every time, you know, they're basically doubling as you're adding up the two previous numbers. So like the Fibonacci sequence, even using this linear algorithm, the number of operations increases linearly, but the amount of time, like real seconds it takes, does not increase linearly. It's much worse than that. And then lastly, this only the largest term matters. This is, you know, generally not true in practical situations. Because one of the assumptions in Big O is that we're only concerned about when n gets really big, like tens or thousands. But practically speaking, lots of times you'll have to, you know, process an array with only 5 or 10 elements. But you'll still find out that your algorithm is, you know, too inefficient and it only can handle 8 of them or something. And it might just be because of constant factors. So like in a lot of these real life situations, if you have very large constant factors while you're processing a small array, small n, it's very plausible that reducing the constant factors is going to make a more meaningful difference in how the function performs and your user's perception of speed. So definitely some contrarian opinions. I don't think this is the most important thing while you're working on the job, but people will definitely ask you about this when you are interviewing. So it's important that you can speak intelligently about this stuff. So I know we've been going over a few minutes. I apologize, trying never to do that. So let me just give you all one last chance for questions before we break for lunch. What questions have we got? Anyone else? Questions, comments?
I think Evan had a question.
What's up?
So my question to Adam was, let me go back in the chat and read it because I forgot. So I was saying, so like, correct me if I'm wrong, but the only time like this really matters is in like interviews when like you might get the question correct and the time complexity isn't optimal. So the interviewer will kind of want you to give the optimal solution. Of course, I haven't been through any real technical interviews, so I kind of defer to you guys. So what's been your experience with that?
Like for the kinds of jobs that I interview for, Big O analysis is not used on the job. It's just that, you know, I'm getting interviewed by people who took computer science 15 years ago and they don't want to let their degree go to waste. So they're going to continue asking people about Big O analysis. But if you're doing work like at a lower level, like if you're writing code for like microchips or maybe like Internet of Things, if you're writing code that gets run like 1,000 times a second, or you just know that you're processing enormous queues of data, then that person should you know more about Big O analysis. But like at the level that we're going to be working at, we're most likely going to be using tools that were written by people who have a stronger understanding of complexity analysis.
Yeah, that's been my experience too. There's a lot of trends in interviewing, and I've never used any of this stuff on the job, but it has come up in interviews because that's how people feel like they can figure out if someone's going to be a productive programmer or not. I do think there's some value in terms of learning it, in part because it's just sort of one of the professional assumptions of the field. So it just kind of puts you on the same page with your peers. It gives you a common language. And also because it develops the skill of that sort of like logical, mathematical, computational thinking. And again, I would use the analogy of an applied skill, like, you know, a musician might practice all sorts of crazy scales. And it's not like then when you go to a gig and you're with the band and playing at a concert in front of people, you're playing crazy scales, but like your overall facility and skill has been like improved to some degree. And I think there's some truth to that. It's not the most important thing by far. I actually think like organization and communication skills are more important. but I think it builds up some of those. I don't know if that makes sense, Raphael. I'm curious what you think.
No, that totally makes sense. I definitely agree with that. Yeah, especially about the like organizational skills and communication skills. Like generally speaking, it's been my experience that when something fails in a web application, when like someone made a mistake, the issue is not that someone was lacking technical skills. Like that happens sometimes. Like, oh, didn't you know about this? You should have done this the other way. But much more commonly, the issue is that someone was just disorganized or didn't express themselves clearly, or just forgot to say something important. So definitely communication and organization, I think, are much more important skills for a web developer than just like the raw technical. Well, I mean, you do need technical ability, but most developers are technical enough for the jobs that they have, and problems arise more commonly from organization and communication.
Totally, yeah. And like if you're good at time management, that's honestly, I feel like a software engineering superpower, and one that I'm not great at. I think a lot of the questions that were coming up in the channel too, I think it is totally confusing that we're covering this stuff and talking about this stuff, and it's covered in interviews, but then for all these other sort of programming problems that we're doing, it's not like directly relevant. And I hear a lot of questions kind of around that, like, well, when do we need to think about this, and when should we care about this? And that makes a lot of sense. And again, I think it's like, I think this falls into the category of things too, where it's like really good to know that it exists. And if you run into a situation with it, like know enough so that you can go deeper. So, but you don't use it on the day-to-day. I think it's more like knowing that it's there. Like you don't want to be the person that ends up writing an SQL query that's doing like nested for loops with terrible efficiency, and none of you will, because we're all learning this now. But someone wrote that, just because they didn't know. And that's a lot of what I think companies are trying to filter for. And then the other piece I think that was hard for me to see until I started working in the industry is that like once you start building applications for real world problems, like it's like an engineering discipline in that like you don't care about the performance of your website until it becomes a problem, which isn't quite true. Like you obviously want to have something that's good and performant, but especially if you're working at a company and there's not a lot of time and there's like, you have to prioritize, like questions of like performance and things like that, I think come up, when they're problematic. I don't know what the right way to describe this is, but I know like engineers are really good at this. They know kind of what they need to optimize and what they don't. And I think I'll just pause there.
Yeah, for sure. I would definitely agree with that. If you don't think you need a super optimized algorithm, just write one that's intuitive, that you can write quickly, and that you are confident works, that you can debug easily. That might be more important than something that runs a little bit faster. So
Yeah. Well, yeah, it's well put.
I like to think that linear algorithms are kind of the gold standard, O of n. You're just looping through an array and doing one operation to each element. That's as simple as an algorithm gets, really, in my mind. And so it may be possible that you can, through some cleverness, speed up that algorithm from O of n to O of log n, but that algorithm is going to look much more complicated. So you have to ask yourself if the extra complexity in writing and reading and debugging that algorithm is worth the speed you get. Maybe it's only ever going to be called like once a year on inputs of 10 or 20 items, in which case the complexity doesn't matter as much as the maintenance.
Yeah. And just to add to that, like people were asking about the project as a whole too. And like with a web app, for example, like if you're looking at performance, this is something I read somewhere, and I think that's really true. Like if in the real world, like you would always ideally want to profile to figure out, all right, where in my program is performance slow? Because you want to work on the slowest part. Like if you take this one part and it's super optimized, but then your database call takes 1 million years, then the rest of it doesn't matter. So it's sort of like in a real world web app, would be you look at, all right, do we have a performance problem? If so, where is it the slowest? And that's where you start. And that's kind of why you don't have to think about or worry about the performance of the whole thing, because you can only go as slow as your slowest piece.
Yeah, that's definitely a great point. I've definitely seen too many developers who get like caught up with, you know, over optimizing something that maybe they don't need to. And sorry, I just lost my train of thought. Forgot where I was going with that.
Yeah, well, I'll just throw in, there's the great saying that is totally true. Premature optimization is the root of all evil. And I think that's a great guide. And it's true. Like, I feel like so many times as a junior developer, I had a cool idea, and it's tough when you're learning because you want to play and explore with cool ideas. And you'll see once you kind of get out, like working in the business environment, you have a cool idea and you kind of do stuff and get ahead of yourself. And then when the thing you're trying to like solve, like if I want to like come up with a cool idea for the account class for this feature that we've got in 6 months, and then when it comes time to actually build the feature, the requirements have changed or you've forgotten about something. So if you're not sure, I think the premature optimization is the root of all evil is a good guide.
You just reminded me that I was going to talk about just profiling real quick. So yeah, I've definitely been frustrated with people in the past who, even like aside from Big O, will try to analyze the performance just like theoretically in like an abstract way or by reading the code. But like by far the easiest, most time efficient way to like analyze the performance of an application is just use it and ask yourself if it feels good. If everything feels fast, then you're done optimizing it. Also, I wanted to address real quickly Garrett's comment over here about different calculations for space complexity and time complexity. So you measure them like kind of the same way. Time complexity is number of operations. Space complexity would be like number of elements in an array or in an object. Like if you need to create a dictionary in order to keep track of things during an algorithm, then you might be sensitive to the size of that dictionary. So let me just give you a really quick example. I'm just going to describe this, but let's say you're looping through an array of letters and you want to count how many times each letter appears. So I'm pretty sure that was like an exact challenge we've given you, looping through an array and counting the occurrences of whatever. And so a naive way to do that is with a nested for loop. Just for each element in the array, you loop through the array again and then count up how many of that thing you find. But that's an n squared algorithm. So that's, you know, really, really slow. And then a way that we've learned to speed that up is by using a dictionary. So for every letter that you encounter in the array, you add it to your dictionary. And then when you encounter it again, you just increment the count in your dictionary of how many times you've seen it. So then you only need to do one loop through your array, but then that also creates a data structure, which is potentially as big as the entire array if every letter was unique. So even though using the dictionary makes your algorithm much faster, it's O of n instead of O of n squared, it increases your space complexity from O of 1, where you don't need any data structure at all, to O of n, where you need a data structure that is potentially as large as the input array. So oftentimes you'll be asked about trade-offs in space versus time complexity. So for that particular example, counting duplicates, you know, you could say that the n squared algorithm is not strictly worse, but it's a trade-off. You're using more space, or you're using less space with the n squared algorithm and taking up more time. Now, in my opinion, you're taking up considerably, you're taking an unacceptable amount of extra time, and and saving a trivial amount of space. So the trade-off is not worth it, but it is a trade-off. So it is interesting to talk about. Okay, so now that's actually everything I have to say about Big O. Thank you for listening to me ranting. And if there are no more questions, this is 30 minutes after a good time to end our lecture for today. So thank you very much, everyone, for listening, watching, being engaged, asking questions. Really enjoy it. We got some exercises for tonight. We've got a guest speaker coming in tomorrow. Stand down is at 5 p.m. tonight. And that's all we've got going on in the near future. So thanks, everybody. Take care.